Hey, everybody. So we are going to talk today about polar coordinates. And so let's actually first start by reminding ourselves about the coordinate system we're probably most familiar with, sometimes called the rectangular or Cartesian coordinate system. Right, and so we usually start. We have a horizontal axis that we often denote with x, and a vertical axis that we often denote with y. And there's a point where they intersect that we call the origin. And the way this coordinate system works, right? A coordinate system gives us a way to identify locations relative to some special point, in this case, the origin. And so if I give you the coordinates, if I give you a point out here and I give you its coordinates, call them A, B, or something like that, then what we're telling somebody is that A is the horizontal distance and B is the vertical distance that point is from the origin. Or you could say the A is the horizontal distance from the vertical axis and B is the vertical distance from the horizontal axis, right? And if we know the conventions, if A is negative, then we go to the left. If A is positive, we go to the right. If B is positive, we go up. And if B is negative, we go down, right? So in general, we have the X, Y coordinates. This is our horizontal displacement. This is our vertical displacement. Okay. All right, so that's the one we're used to. So this isn't, and in this system, right, we have our origin at 0, 0. This isn't the only way to describe location. And we're really used to this, and this is, in my experience, the most widely used coordinate system. However, in everyday life and in certain corners of math and science, there's an actually much more convenient way to describe where a point is. Right? So we're still going to start with a special point, though sometimes this is called, in this system, the pole. It's also called the origin sometimes, right? So it just depends on who's talking, but you might hear it referred to as the pole, the center of this coordinate system. And instead of telling somebody how far to move right or left and up and down to denote a point, we tell somebody how far to go and in what direction, right? So if I point you in this direction and tell you to a distance to go, that lands you in a specific point, right? So we might write two coordinates, but they mean different things, right? The first number, so let's write this out, in our polar coordinate system, right? Instead of x and y, we usually think of them as r and theta, right? The particular symbols don't really matter. We just need to know that we're in the polar system because in both cases, look, you're going to have two numbers listed, but the meaning is very different. In the rectangular coordinate system, the first one tells you what to do horizontally. The second one tells you what to do vertically. In the polar coordinate system, the first coordinate tells you the distance from the origin, and the second coordinate tells you the direction, right? This is much more in line with how we usually describe position in real life, right? If you're standing with a friend in a field and you see a bunny hopping through the grass, you point somewhere and try to estimate how far away it is. Look over there, about 20 yards. I see a rabbit. right? Very few of us would be like, imagine going 5 units, 5 yards to the right and 15 yards forward. Do you see the point I'm talking about, right? That'd be an awkward way to do it. It's very convenient when you're working on paper. But so this is our polar coordinate system, right? The way we measure direction is the way we've been doing it to set up our sine and cosine functions, right? So when we say direction theta, the normal convention that we've been doing all this time applies. We place our angle. So in the example I gave, theta, right? That's how we give the direction. 0 is along the horizontal axis to the right, and theta increases as we go counterclockwise. And so whatever theta is, that tells you the direction that you're going. Okay, so let's do an example. Let's give some actual coordinates, polar coordinates. So here's a nice set of axes, an okay set of axes. So let's take a look at the point, for instance, 3 pi over 6. Okay, so this is r is equal to 3, theta is equal to pi over 6. This means we're 3 units from the center. So here's our center. So let's just make, let's say 3 units is about this far away. Now think about what that means. Without knowing the direction, these are all the points that are 3 units away, right? Of course, pretending that's an actual circle, right? So r equals 3 gives us a circle that our point can possibly live on. But then we find out that theta is pi over 6, right? We know that theta over pi over 6 is in this direction, and that puts us, all right, so here's our line with an angle of pi over 6, and that puts us at a point in space 3 units away from the origin in that direction. Okay, sorry that circle is so horrible, but that's the best I could do. Okay, so again, we're pointing ourselves in a direction and telling somebody how far we want to move in that direction. All right, so let me fix this 6. Now, we know exactly what we mean when we say something like a negative angle, right? We've already established this. So if I gave you the point 3 negative pi over 6, we of course mean now we're just going to go in this direction. Whoops, let's try to make it a little more similar, symmetric. So the same angle, but negative. The point, this is the point 3 negative pi over 6. Okay. What about a negative r? Well, the simple choice to make, if I graph the point negative 3 pi over 6, well, that's the same direction, right? That's this line here that we came up with before, pi over 6. And when we had 3 as our r value, or sometimes thought of as the radius and theta, so we went 3 units along that line. When it's negative, we just go in the opposite direction. And there's 3 units away, again, on that circle, pretending that actually looks like a circle. So instead of going forward in the direction, it's going in the opposite direction. Okay. Let's compare that to another point. Let's compare that to the point 3 and 7 pi over 6. Okay, let's label some of these. So let's just use, we'll call this A, call this B, let's call this C, call this D. So here's A, here's B, here's C. Now let's think about what D is. So D, again, the radius is 3. I know it's on this circle where all the points are 3 units away. And I want to be 7 pi over 6 away. So let's think to ourselves, 7 pi over 6. Well, this is just pi over 6 plus 6 pi over 6, right? That's just pi, or pi over 6 plus pi. So that's like starting at this angle here and adding pi to it gives us a half rotation. That's going to put us, so our direction now is this way. We move 3 units out. We land exactly on the point C. So these two configurations, or these two coordinates, are the exact same point. They describe the same location. Okay? So this is something very different with polar coordinates than rectangular coordinates, that there are an infinite number of ways to describe the same location, right? So for instance, we could also do 3, and let's add another 2 pi to the, or let's add 2 pi to this, so we'd have 19 pi over 6, right? That's again the same point, and I could keep playing this game, or we can go in the negative direction, and we can play with these negative radii and things like that, these negative r values. So there's an infinite way to write down any point in polar coordinates. Unless there's a good reason to, we will typically choose r to be positive and theta to be, say, between negative 2 pi and 2 pi, right? So we'll see negative theta fairly often. I guess 0 to 2 pi is the most common, but we'll certainly see negative theta. But we don't typically choose a value like this, right? If we're just trying to describe a location, wrapping around doesn't usually make sense. Once in a while you might see it because there might be a reason for it. We might be trying to imply something else, but let's not dig too deep into that. Okay, so that's a distinct feature of polar coordinates, that they are not unique in describing a location, and there are infinite ways to describe the location. One other thing is we typically write the coordinates of the origin as 0, 0, same as in the rectangular coordinate system, but in this case, what do we mean? We mean 0 units away from the pole, the center, the origin, right? This is our r, theta, in the direction of theta. Well, really, it doesn't matter, right? Because if we're moving no units away, it doesn't matter which way I'm facing. If I don't go anywhere, I'm still right here. 0, 0 is just the easiest one to use. So, right, 0 pi over 2 is also right in the center, or 0, a billion is also right in the center. But 0, 0 is the most typical thing we'll write down there. Okay, now let's see how we can connect Cartesian and polar coordinates, right? In other words, what I want to do now is see, how do I go from one to the other? Okay, so let's start this way. Let's suppose we are given polar coordinates, right? So we're given a distance and an angle. All right, let's draw a little coordinate system. Okay, there's our center. So if we're given a point r theta, let's just put the point somewhere out here. All right. So what I'm describing, remember, what I'm telling you when I write r theta is oops, I didn't want that to move. There's a line connecting the origin. What I'm telling you when I give you the coordinate r theta is that this line segment from the center to that point is a distance of r, and this angle is theta, right? What if I wanted to tell you the rectangular coordinates for this? In other words, how far is it horizontally from the y-axis, and how far is it vertically from the x-axis? I don't know why I drew this down here. Let's just draw right at the point. All right, so I might want to know these two distances. So how can I get them? Well, let's do this. Let me clear this out a little bit. Let's suppose what I'm about to do will work whether or not r is bigger than 1 or not. But for the sake of this drawing, let's suppose that r is bigger than 1. Well, I know if I draw a unit circle, so this is now a unit circle, that this line intersects the unit circle at the point, this will be cosine theta, sine theta, right? Remember, this is the angle theta, right? So we know that this point here is cosine theta, sine theta, right? That's how the unit circle works. So let's just think about these triangles that I have here. So there's the big triangle. This is out to the point r theta. So this is the one where the distance, all right, let me make this drawing a little nicer, sorry. And let me use these colors. So there's the big triangle. Okay, this is the point we've called r theta out there. And remember, we know this distance is r. Okay. Now we also have this smaller triangle that lives right on top of the little corner of this one, right? In this triangle, we know these coordinates, but let's think of them instead. We know that this distance here is cosine theta. Well, it's a negative distance because we're going to the left. And we know that this height here is sine theta, okay? And we also know that the hypotenuse of this triangle is 1. Well, what does that mean? That means if I scale this small blue triangle, if I multiply everything by r, I end up with a hypotenuse of r. This side will be r cosine theta, and this side will be r sine theta. That's exactly the distances we were looking for. This bottom edge is going to be the x-coordinate, and this vertical edge is going to be the y-coordinate, right? It's the vertical distance and the horizontal distance. So what that tells us, let's sum this all up. Here's the important part. If we are given polar coordinate r theta, we can convert to rectangular with x equals r cosine theta, y equals r sine theta, right? So you have r and theta, you plug them into these formulas, you now have an x and a y coordinate. So let's do a couple of examples, and let's use a unit circle to verify, or at least convince ourselves it's true. So let's get our red going. A little thicker maybe. All right. So let's start with a couple points on the unit circle. So given points r theta, so we'll do r theta over here, and we'll convert them to rectangular coordinates. All right, so let's start with the point 1 pi over 2. Okay, so this is a point 1 unit away in the direction pi over 2, right? So we remember pi over 2 is a right angle pointing straight up. So that point is going to be right there. So in polar coordinates, this is 1 pi over 2. We can see clearly from this from our unit circle knowledge that that's at the point 0, 1. But let's use the formulas to let's verify that this works with the formulas, right? So given 1 pi over 2 as our r and theta, x is equal to r times cosine of pi over 2, and y is equal to r times sine of pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. 1 times 1 is 1. And so we're given the point 0, 1, right? So 1 pi over 2 in polar coordinates is the point 0, 1 in rectangular coordinates. Let's do another one. 1, 0. So in polar coordinates, that's 1 unit away in the 0 direction. That puts us right here. Well, this is a funny one because in rectangular coordinates, that's exactly the same, right? If we use our formula, x is equal to 1 times cosine of 0. Cosine of 0 is 1. 1 times 1 is 1. Y is equal to 1 times sine of 0. Sine of 0 is 0. So this is 0. So in this case, they're the same numbers, but they are still representing different things, right? This is my horizontal distance. This is my vertical distance. In the polar coordinates, it's our distance from the origin and our direction using our standard model for making angles, our standard definition for angles. All right, let's do a couple others. Let me write our conversion again. R theta, we'll get to xy with x equals r cosine theta. Y equals r sine theta. Now let's draw another coordinate system. This time we'll do ones that don't happily live on the unit circle. So let's start with the point, what do I have? 2 and 5 pi over 4. Okay, so first let's try to locate this. So 5 pi over 4, let's find our direction. So 4 pi over 4 is just 1 pi. That would be halfway around the circle. I'll draw this one in. There's our initial side. 5 pi over 4 will be there, right? So there's our theta. And we go 2 units out. So I don't have a scale on here. I'm just going to pick this to be our point, 2 units out. Okay. Let's convert this to rectangular. We'll have x equals 2 cosine 5 pi over 4, and y equals 2 sine of 5 pi over 4. 5 pi over 4, if you look at the unit circle, or remember, is the same as sine of pi over 4. They're both root 2 over 2. So we get the point, we get the x coordinate of negative root 2, the y coordinate of negative root 2. So this is the point, negative root 2, negative root 2. Notice it seems reasonable based on our drawing, right? They're both negative. That's the right coordinate, the right quadrant for them both to be negative. And if you draw yourself a little isosceles triangle there, you'll see that with the x and y sides being square root of 2, you'll see using the Pythagorean theorem that that distance, the hypotenuse, is going to be 2. Okay, let's do one more point. Let's do one more. So let's do the polar coordinate 4 pi over 3. All right, so let's draw again. Here's our initial side, pi over 3. Looks like I'm going to need a little more space. Let's move this guy down. So pi over 3 seems about right. Well, trying to make this about the same scale, I think maybe about right there. is about 4 units out in that direction. Let's convert this to rectangular. X is going to be 4 cosine pi over 3. Y is going to be 4 sine pi over 3. Cosine of pi over 3 is 1/2, so we get a 2. Sine of pi over 3 is root 3 over 2, so we end up with 2 root 3. So this becomes 2 root 3 in rectangular coordinates, right? They're both describing the same point, right? The green here is telling you the direction pi over 3, so along this line, go out 4 units. The black 2 root 3 is telling you to move 2 units this way, and then 2 times root 3 units up to get to that point. They will land you in exactly the same point, at exactly the same point. Okay, notice also when you're looking at these, right? So maybe the 4 pi over 3 is a clue that you're in polar coordinates, but it's still just a number. It doesn't have to be, right? And somebody could write 4, 1 to mean 4 units in the direction of 1 radian, which is a similar direction to this, a little bit smaller, right? And there's no way to tell if you're looking at rectangular polar coordinates, so it has to be told what it is, right? Or within context, right? If you're working in polar, then assume it's polar. But it should be stated explicitly what you're doing. We use r theta often to signify this to people that we're doing polar coordinates. Okay, now let's work out how to move in the other direction. If we're given rectangular coordinates, how do we convert to polar coordinates, right? So we will often find reasons that we want to go back and forth between the two. Sometimes switching from one to the other makes a problem dramatically easier, okay? And we'll see some examples of that in this series of videos, though some of these things happen further down the line. Okay, so let's again start with a coordinate system. And suppose I'm given a point xy. Let's just put it here. There's the point xy. And let's say we want to convert this to r theta. So we need to figure out 2 things. We need to figure out the distance it is from the origin, okay? Well, we know a distance formula. The distance a point is from the origin is the square root of the sum of the squares of its coordinates, right? This is just a distance formula where 0 is the other point. You can also think of the Pythagorean theorem if this is one side of your triangle, this is the other side of your triangle. Well, that distance we just said is r, so let's just call it r, right? That's the distance, but we're in polar coordinates, we're just using the symbol r. For various reasons, it's typically written as r squared equals x squared plus y squared. Just to, for whatever reason, this is the way that people typically write this down. That r squared is equal to x squared plus y squared. Partially, it gives us the fact that it could be negative r, and then we get a different theta, but we'll typically take the positive solution anyhow. Okay, so that's the r. This, right, if you're given coordinates, these are numbers, you can find r given them. What about theta? Well, here's what we're going to do. We know already the connection between the x and y coordinates and angles to some extent, right? We were already given that y is equal to r sine theta. I didn't mean to write that so far away. I need space. Y is equal to r sine theta, and x is equal to r cosine theta. So that makes this true. Y over x is equal to r sine theta over r cosine theta. right? Well, those r's cancel and we get sine theta over cosine theta, which we know to be tangent theta. So let's just write down that result. Y over x is equal to tangent theta. And then, of course, we can take, let's just put these together. We can take the inverse tangent of this to get theta. Okay. Now, I'm going to put a little asterisk here because there's a slight hitch in what we've done here that we'll get to in just a second. So let's do an example to make this a little bit clearer. So let's say, let's put our examples on here. So let me get rid of this. Let's say I have the point 3, -3. So here, let's do this right. I'm gonna erase this and do it using the little dots. I use those just to keep my writing straight, but why not use it for this as well? Okay, so let's go to the point 3, -3. So 1, 2, 3. Let's make each 2 dots be a unit because there's 3 units out. 1, 2, 3 units down. So here's the point 3, -3. So I want to describe that with r and theta. So r is going to be equal to x squared plus y squared. So I've got my x and my y. Sorry, r squared is equal to x squared plus y squared. So this is going to be 3 squared plus -3 squared. So that's 18, which means r is the square root of 18, which is 3 root 2, right? Now, I could take plus or minus to solve this. There's no reason right now to take negative. There's seldom a reason to take the negative, so we'll take the positive square root. So there's our radius. We want something that's 3 square root of 2 units from the origin. So you can imagine a circle. 3 square root of 2 square root of 2 is like a little smaller than 1.5. So this is somewhere between like 4, 4.5 distance away. So you can sorry, I'm just trying to see if that, yeah, sorry, I had a little moment. So you can imagine the circle that distance is telling us, right? We already know where this point is because we started with a point, but just kind of to give us the picture, the information we have so far, if you draw a circle with its center at the origin through the point we have, those are all the points with r 3 root 2. Okay, how about theta? Well, we take y over x in this case. So we've got tangent of theta is equal to y over x. So y over x is going to be -3 over 3 or -1. Take the inverse tangent of this. The inverse tangent of -1 is -pi over 4. Right? So if you think about -pi over 4, that's an angle about right there, which is what we expect. This is our -pi over 4. And you can eyeball this distance, at least seems reasonable, right? Of course, you know, this is the correct point. So this point, 3, -3 in polar coordinates is going to be 3 root 2 -pi over 4, right? This is r, this is theta. This set of numbers is x and y, right? Again, if I don't tell you that, there's nothing inherent in these numbers that tells you one's polar and one's rectangular. You have to tell somebody what set of rules you're using to describe the point you're at. All right, let's do one more to get to the little issue we have, why I have this little asterisk here. Let's look at the point, a very similar point, -3, 3. So now -3 in the x coordinates. So 1, 2, 3, and then +3 y coordinate puts us right here. -3, 3. So we'll do the same conversion over here. R is going to be the square root of negative 3 squared plus 3 squared is going to be same thing, 3 root 2. Tangent of theta is going to be y over x, so 3 over negative 3. So that's tangent of theta equals negative 1. So theta is tangent inverse of negative 1, which is negative pi over 4. This is obviously a problem. We've just taken a very different point and spit out the opposite, we've taken a very different set of rectangular coordinates and spit out the same polar coordinates as this point that's not even in the same quadrant, right? So this cannot be correct. This cannot be correct, right? Because these two things that we've got over here, the radius and the theta, are pointing at the same point here. So there's two ways we could fix this. One would be to take the negative radius, right? Because then we're pointing in the direction of this green line, but going backwards, and we'll land there. That's not the typical way to do, right? It's kind of not a very intuitive way to do things. It's like trying to describe how to tell somebody how to get somewhere and saying, okay, face this direction and then walk backwards, right? It's just kind of an odd way to do things. So there's a different convention that we will use. Here's the problem. Tangent inverse of negative 1, right? The inverse tangent only ever gives us angles between negative pi over 2 and pi over 2. Those are in quadrants 1 and 4, right? But for every angle over here with a tangent of negative 1, we just found there's another angle in this direction that also has a tangent of negative 1. Right? This one is over in quadrant 2, and we'll find a similar thing in quadrant 3, that angles in quadrant 1 have the same tangent as angles in quadrant 3, right? Remember, they're y over x. When they're both positive in quadrant 1, you'll get the same values as when they're both negative because they come out positive, right? Or like what we saw here, where in the first case we had y over x was negative 3 over 3 is a negative 1. Here we have a 3 over negative 3 is still a negative 1, where the negative was switched, but the result's the same. So when our rectangular point is in quadrant 2 or 3, we have to adjust this. Okay, we have to adjust this situation. What we want to do is simply add pi, because that's going to take us from this negative pi over 4 over to here, right? So we add pi to this, and that gives us 3 pi over 4. And so this rectangular coordinate, 3, negative 3, goes to the polar coordinate, 3 root 2, what did I just say? 3 pi over 4. Okay. Now, there's nothing wrong. I could have written negative root 2 pi over 4. This is pointing at the right point, but the convention is we make the change in the angle. Okay, that's the convention that people use. So I'm not saying this is wrong. It's just not typical and seems like a strange way to describe a point. Look over there, go backwards, right? That's a weird way to do things. So here, let's finish with this. Our rule for converting. So let's just write them both down, just to have them all in one place. So to convert, let's start with convert Cartesian to polar. Given the point x, y, we find r theta by, so we'll have two things. R squared is equal to x squared plus y squared, or equivalently, r is equal to the square root of x squared plus y squared. And theta will be the tangent inverse of y over x if the point is in quadrant 1 or quadrant 4. Theta is equal to tangent inverse of y over x plus pi if the point is in quadrant 2 or quadrant 3. Okay, so we have to add this little confusion at the end here, right? But if you understand our restrictions for the inverse tangent and have a picture of this whole thing, you can see what's happening. We're just spinning around by 180 degrees, adding that pi when we want to get to the other side. And then finally, let's just put this next to it just to have them all in one place. If we convert polar to Cartesian, given the point r theta, find x, y by x equals r cosine theta, y equals r sine theta, right? This one's a little more straightforward. Okay, that is it. Thank you, everybody. We'll do more with these in future videos, but that's it for now. I will see you next time.